Good morning, everyone. Welcome to the 34th Trustworthy Young Scientist Seminar. I am Feng Liu, a researcher from Recon AIP and the University of Melbourne. Today, I'm going to host the seminar. The Trustworthy Young Scientist Seminar is a video series that features young scientists giving talks and discoveries in relation to trustworthy machine learning. This network is funded by Recon AIP, GST, and ACTX. The full name Recon AIP is Recon Center for Advanced Intelligence Project. AIP was founded in 2016 as a research center for the Mixed AIP project. AIP Center conducts the Japan's leading AI research, which is headed by Professor Sugiyama. AIP aims to enhance AI fundamental technology and its real-world applications, and encourages the collaboration with various researchers and engineers in the related fields. In this seminar, we are pleased to host Sharon Ishendi, who is an assistant professor at the University of Wisconsin-Madison. Previously, Sharon was a postdoc research fellow in the computer science department at the Stanford AI Lab. She completed her PhD from Cornell University, where she was advised by John E. Horkoff. She has an organization of an ICM workshop on uncertainty and robustness in deep learning in 2019 and 2020, and has served as area chair for NeurIPS, ICML, iClear, and Trivial AI. Her broad research interests are in deep learning and machine learning. Her research focuses on developing machine learning algorithms that can function safely and reliably in the open world. She is a recipient of Facebook Research Award, Google Research Award, Amazon Research Award, and was named Forbes 30 Under 30 in Science. Today, Sharon will share her recent research advances regarding the out-of distribution detection. Welcome, Sharon.
So I would like to start the talk by showing you this video. This is a model trained on the Berkeley Deep Drive 100K dataset, performing bounding box tracking on the road. And whenever we see videos like this, we may get overly positive impression of how remarkable deep learning models have evolved to be, which are true in a lot of cases. And in my research, I encourage researchers and practitioners to look at the other side as well, to take a cautious view at the methods and technologies that we built, especially be aware of unexpected situations that the model wasn't trained for. And hopefully by the end of the talk, we can see things in a more well-rounded perspective. So I know there are many experts in statistics, machine learning, and AI in the audience. So I would encourage you to maybe, let's think together how you would build such a self-driving car model, right? And so the typical process to abstract things a little bit is to start with this training data, where we have this corresponding labels, in this case, pedestrian, cars, and truck, right? Each of this object would be individually annotated. And then we would train on our favorite machine learning model, say a neural network. Here, this output typically contain these predefined categories. And once you go through all this steps in terms of developing the model, let's say finally you reach a model that you are happy with the performance and you think it's ready to be deployed. This is where some of the unexpected trouble would kick in. And why do I say that? Because in classic machine learning assumption, we would expect, right, the test data to match this training data distribution. But in reality, right, these two data distributions can be wildly different, and a lot of unknowns can emerge. So we call this the open world setting, in contrast to this closed world machine learning. For example, in our recent work, we took this image from the MS COCO data set and run through this self-driving car model that was just trained on the BDD data set. So you can see that the model would produce overconfident predictions for this unknown object, the helicopter in the middle, right? being predicted as a truck. And keep in mind that this helicopter was never exposed to the model during training time. So in other words, deep networks do not necessarily know what they don't know. And this has raised significant concerns on models' safety and reliability. As you can imagine, algorithms that blindly classify the out-of-distribution samples into one of the known classes can be catastrophic. And ideally, we want the model to be able to flag such scenario so that the human driver can take precautions in this case. And to give you a concrete example, right, in real life, I'm quoting this news article from April this year, which reported that a Tesla vehicle crashed into this private jet that is worth 3.5 million. Fortunately, nobody got hurt in this incident, but you can imagine the gravity of the issues and the safety concerns that this could cause. And so this out of distribution detection problem has become very, very important, and this is going to be the focus of my talk today. And so what is out of distribution data? You might be asking. And I want to start by providing this simple definition. Let's say we have our training data distribution that is a mixture of two Gaussians with class label y equals to 1 and y equals to -1. And our in distribution Pn would be the marginal of this joint distribution defined over the input space x times the label space y. And during test time, these orange dots could emerge, which are out of distribution from an unknown class that doesn't belong to either y equals to 1 or -1, and therefore should not be predicted by the model. And to translate this toy data into some high-dimensional images, you can think of, for example, cipher 10 on the left-hand side being the in distribution, and SVHN or Street View Housing Number dataset being the out-of-distribution dataset, which have disjoint labels. Well, you might think that this OOD is way too obvious to us, but I'm going to show you how such an easy setup could trouble the state-of-art neural networks. And later on in this talk, I'll also discuss how we can go beyond such simplified definition. So let's start with this simple view and build from here. And so SVHN is just one of the OOD that the model would encounter in this open world. And there are, of course, many other unknowns on this complex data manifold. So this is an image from a recent talk by OpenAI, which I think very nicely illustrates the complexity of the problem. So the right-hand side would contain all the possible images that one would encounter and maybe generate on the internet. And this is in a sharp contrast to the left-hand side, which is the task-specific data set, in this case, cipher 10, right? And so out-of-distribution detection is a hard problem, and I would like to use a few slides, first explaining the why, before we get into the how, the solution. So the first challenge is the lack of supervision from unknowns during training. And the model is typically trained only on the in-distribution data, in this case, the green and blue dots, using empirical risk minimization. And you can't really anticipate where these orange dots could emerge in advance, because there can be a huge space of unknowns, especially in the high dimensional space. And the problem is further exacerbated by the high capacity neural networks that we're working with nowadays. And to illustrate my point, let's consider this example at the bottom of the slide, where we have this in-distribution data that is a mixture of 3 Gaussians colored in gray. And so if you were to train a neural network to classify these three classes, right? This would learn a decision boundary that has this triangular shape. And so this model would almost perfectly distinguish these three classes in terms of classification accuracy. So that's great there. But what's problematic is when it comes to out of distribution detection, you would realize this decision boundary is ill-fated, that cannot distinguish between ID versus OOD. For example, if you look at those red region, which corresponding to data points that are far away from the in distribution, those three gray clusters, right? But they could trigger the model to produce a very high output, which is undesirable. And you might also be wondering, well, can we perform density estimation using deep generative models to directly estimate P of X, which is a very, very natural idea. It turns out there are unique challenges there too. For example, training generative models can be difficult to optimize. And moreover, they don't provide classification ability, which is something we care about. And one last challenge I want to highlight here is that real-world images are composed of numerous objects and components. And for example, in this picture, this helicopter is the out of distribution object, whereas you also see many other in distribution objects, such as pedestrian cars and so on. And therefore, we need this finer grained understanding of OOD at the object level, moving beyond this image level. And over the years, we have seen this surge of interest in this challenging problem space. And it's really great to see a thriving literature on out of distribution detection. And recently, we have composed a comprehensive survey that tries to cover some of the methodologies developed in the space in the last few years. And I'll try to unpack some of these in this talk. And by the way, feel free to interrupt me, unmute yourself if you have any question during the talk. I welcome questions at any time. So the earliest work adopted this post-hoc approach for out-of-distribution detection. And let me give you a method overview. So here the model is typically trained on the in-distribution data, say Cypher10, using empirical risk minimization. And once the model is trained, let's take the network as it is without modifying its parameters. And so during inference time, for any given input, we're going to devise a scoring function called S for OOD detection. So essentially, we're performing level set estimation based on the scoring function. And if it's below certain threshold lambda, we're going to reject this input. And otherwise, we'll produce the class prediction as usual. And so the advantage of post-hoc OOD detection is that it doesn't interfere with our original task or the model that's already been deployed or running in production that may be hard to replace immediately. So in this case, the model is guaranteed to have the same performance in classification while having this additional safety layer almost for free. And this problem is also different from anomaly detection, which is a classic problem in machine learning, which often treat all the data as one class without necessarily differentiating the class labels. And so in this case, we actually care about two things, right? We care about performing classification accurately. And on top of that, we would like to differentiate between in distribution versus out of distribution. So that's the setup here. And so a common baseline is to use the Softmax confidence score, which is also the largest posterior probability as shown here. However, it doesn't really work well. And if maybe some of you have already, worked with this scoring functions before, you would notice that there is one significant issue, is because the network tend to produce the overconfident predictions. And so what happens is if you take a whole collection of ID images, right, say cipher 10 and a whole bunch of OOD images and calculate this or plot this distribution, there is a non-trivial portion of data with very high confidence score concentrated around 1, as highlighted in this red circle. And therefore, you can't reliably draw a threshold somewhere, right, to separate these two distributions. And so that's what makes this problem very challenging. And so in our NeurIPS 20 paper, we put forward an energy-based out-of-distribution detection framework, which has the core idea that influenced many of our recent works. And so compared to the confidence score, I'll talk about later that energy score can in fact be better suited for OOD detection, both empirically and theoretically. And so here is the high level view. Let's say we take a test time input X, and it goes through this network parameterized by theta. And then we calculate this energy score, which I'll talk about the definition in the next. And then based on this energy score, we can perform again a thresholding comparison. And so here we flip the sign of the energy just to align with the convention that the larger score indicates more ID-ness and vice versa. And so now let's dive a little bit more into this how energy score works. So energy-based model was first introduced to machine learning in the 80s. It has been around for decades. And to give you some background, an energy function would take an input X, say my cat, and the corresponding label Y. And then this would produce a scalar. And so this energy essentially measures the compatibility between X and Y. And this would return a lower value if this input and the label is compatible, right? In this case, which would be low, and it will be higher otherwise. And so this function can be non-probabilistic, and you can turn it into a probability density by using this Gibbs distribution. And again, the slide shows the same Gibbs distribution in the previous slide. And so if you look at this denominator, which is also known as the partition function, it takes this integral over all the possible y's. And by equalizing these two sides, we can derive this free energy for any given input in terms of this formula, which is the negative of the log partition function. And so far, nothing is new here, right? This definition of free energy has been around for a long, long time. It's all classic concepts. And so how is this energy-based interpretation or model related to neural networks? It turns out a neural classifier can be interpreted from this energy-based perspective. And for example, let's consider a neural network, which is producing output logits, F1, F2, and so on. And so this is pre-Softmax. And now we can pass this output into the Softmax function, which would produce this normalized probabilities, P of Y conditioned on X. And so here is the definition of Softmax, which I'm sure every one of you is familiar with. And so now if we define this energy function, E of X comma Y, to be the negative of this logit output, effectively, this turns into something that we just saw earlier, right? So you can see some of this kind of symmetry here. And so recall this is how free energy is defined. And in the context of a neural classifier, the free energy replaces the integral with the summation over k different classes. And so now for every input and a neural network parameterized by theta, this energy function can be calculated using this log sum exp operation, which can be very easily computed. And so the key idea of in this work is to really rely on this energy score for OOD detection. And with energy scores, we see that the distribution in this case becomes much more separable between ID versus OOD. And in particular, the in distribution no longer have this the spiky distribution that concentrate around 1, like we saw in the Softmax score case. And here I also want to kind of put this definition of softmax function and energy on the same slide. So you can see some of the inherent connection here. And so this green box, right, this green box highlights this denominator in our softmax function. And so energy score really is the negative log of this denominator, right? And so you see this inherent connection to the log likelihood. It's not exactly equivalent. And that's something, you know, I will actually touch upon in later of my talk, how we can capitalize on this. But for now, I just want to signpost of this inherent connection here. So to evaluate and compare this approach with softmax confidence score, we can train a model on cipher 10 as in distribution and evaluate on SVHN as OOD. And so we can measure the performance in terms of FPR 95, which is the fraction of, excuse me, of OOD that's misclassified as in distribution when 95% of the in distribution data is above the threshold. And so lower FPR is better. And so when we use softmax score, this FPR is roughly around 48%. And in contrast, if we adopt energy score, this FPR can be reduced by more than 13%, which is significant. And this slide shows kind of more expensive evaluation across more OOD data set. And the blue bars are indicating the softmax score, and green bars are based on energy score. And so we observe this consistent improvement on cipher 10. And so in the next 2 slides, I want to provide some explanation for why softmax score is suboptimal for OOD detection. I won't go into the details here, but you know, a lot of this detail is discussed in the paper. And in particular, we can analyze, right? So in a nutshell, we can analyze this training dynamics of neural networks in terms of how they change the energy state of the output. And so in particular, we can derive this gradient of the loss with respect to the parameters, theta. And you can skip this derivation, but what I want to highlight is that this training process, the training dynamics, essentially push down the energy for our training data, right? And so energy would become lower over the course of training for in-distribution data. And so now, if we look at the softmax score, or more precisely, the log of the softmax, it can be decomposed into the summation of 2 terms. The first term is the energy, E of X, and the second term is the maximum logit. And recall that the first term, right, is going to be lower for in distribution, and the second term is going to be higher. And so the summation results in a biased function that's not suitable for OOD detection. And so we can make this analysis even more precise. And to do that, we can adopt this simplified in distribution model. In this case, a mixture of multivariate Gaussian distribution with equal priors, 1 divided by k, and covariance matrix sigma. And this simplicity is desirable because it allows us to precisely characterize the behavior of different OOD scoring functions, in particular this maximum softmax confidence versus the energy. And specifically, this class conditional density is given in this form. And so based on this in-distribution data model, we can derive this Bayes optimal classifier. And here, this posterior probability, P of Y, taking on this class label I, conditioned on the input X, is given in this form. This is just to plug in this class priors and class conditional density. And so now we can see that if we plug in this definition of energy, this energy is, in this case, aligned with this log density. And in contrast, we can also write out this exact analytical form of Softmax score, which is the maximum posterior probability. And you can see that it's not aligned with this log density. And our analysis can be extended into deep networks by modeling the feature space as a Gaussian mixture model as well. And we can show more rigorously and bound this OOD detection performance with respect to different OOD distribution properties. But for the time being, I won't go into further details here. And lastly, I just want to show this very simple one-dimensional toy example that I think makes this explanation very easy to understand. And so in the middle, we have this gray line. That is the ground truth density, density function P of X in 1D. And so this is a mixture of two Gaussians with the modes concentrating around 2 and -2. And so this top of this dark blue line is when we calculate this MSP, right? Maximum softmax probability. And so if you look at this, the top of the curve and notice that the two sides highlighted by this red shade, those corresponds to the false positives, which are the points that have very low likelihood, right? The P of X is very low, but they would trigger this MSP score equals to 1. And so those points would be misclassified as in distribution. And because it's not aligned with this density function. And so in contrast, the bottom line is when the level set kind of aligns with the density function. And so I would like to also use maybe the remainder remainder half of the talk, sharing some of the interesting, I would think, open questions and opportunities moving forward around OOD detection. And so far we have shown, some algorithmic solutions to OOD detection. But a question that is left a mystery is why neural networks, right? This is the question that also bothered me for a long time, is why neural networks produce this overconfident output for OOD data. And answering this question requires us to carefully examine the internal mechanism by which the network is trained and evaluated. And so in our NERPS paper last year, we provided some interesting insights on the plausible cause and mitigation of this overconfidence issue. And this is joint work with my PhD student, Eo Sun and Tran from Facebook AI Research. And so to explain this, this phenomenon, I would like to first recap and remind folks on this batch norm technique, which is one of the most commonly used technique in training the model neural networks. And so here's how batch norm works. During training time, the network would estimate the running mean and variance for each of the unit inside this neural network. And this is estimated based on our training data or based on the ID data. And then during inference time, the network would then apply these batch norm statistics, right, these mean and variance, which would then help normalize the activation for the test data to stabilize the training. So that was the original motivation of how batch norm was invented for. So everything worked fine if you're going to be testing on this, data set that comes from the same IID distribution as the training data. However, our key insight here is that using this mismatched batch norm statistics, right, that are estimated on the ID data, but blindly applied to the OOD data, can trigger abnormally high unit activations and consequently model output. And so this mismatched batch norm statistics actually mess things up when our test data is OOD. And so now we can, let's examine this activation pattern of neural networks in more detail here. This figure shows the distribution of activations in the penultimate layer of a ResNet trained on ImageNet. And so each point in this x-axis corresponds to a single unit, and there are 512 of them on the penultimate layer. And so for each of the units, we would then, calculate this mean and standard deviations that are, can be estimated on this entire ImageNet data set. And so this is shown by this solid line and shaded area respectively. And then we can look at on average how each unit responds to the OOD data, for example, from iNaturalist. And these images do not belong to any ImageNet category. And so here, again, we plot this mean and standard deviations in solid gray line and the shade. And so now if we put these two together and contrast this activation pattern between ID and OOD, we can see that the activation for ID data is well behaved with the near constant mean and standard deviations. That's because, batch norm is supposed to normalize things properly. And in contrast, for the OOD data in gray, the mean activations has significantly larger variations across units, and it's more chaotic, right? As you see from the pattern. And it turns out such high unit activation can undesirably manifest in the model output and causing overconfident predictions on OOD data. And so this observation on unit activation leads to this method, which is quite simple but surprisingly effective, called rectified activation, or REACT. And so our key idea here is to perform post-hoc truncation to the unit activation at a certain threshold, C. And this can be done on any pre-trained model without modification to the training process. And so this REACT operation is applied element-wise to this feature vector h of x. And h of x is the penultimate layer feature. And a higher C would indicate a larger threshold. And in the extreme case, when C is infinity, that would restore all the original activation. And lower would, truncate more information. And so after this truncation, we can then derive this model output, this logit output, by multiplying with this this matrix W. So it's a fully connected layer. And then during test time, REACT can be leveraged by a variety of downstream OOD scoring functions that depends on this F of REACT. And the sample with smaller score would be classified as OOD and vice versa. And so in this chart, we show that REACT can be flexibly used with different OOD scoring functions, and including, for example, the Softmax score and energy score that we have talked about before. And so this green bar would indicate the performance after applying this, this REACT operation. And all of these scoring functions would derive the OOD score directly from the model output f of x, right? So that's where this REACT would have a direct impact on. And so we can see that this operation consistently improves the performance on this original scoring function with and without REACT. So I think I see a chat here. Let me see if I'm able to pull this up. Or if you would like to unmute yourself and ask, you're more than welcome to do so as well.
Hi, thank you for introducing your interesting work. My question is REACT applied during training? I may miss the details, but I just want to clarify. Yeah, is REACT applied during training time?
Yeah, thank you for that question. So to clarify, REACT is applied in a post hoc manner for a pre-trained model during the test time. not during training time. And so
Okay.
the training is done, let's say, using the typical training process with the loss functions, let's say cross entropy in this case.
Great. And I remember you introduced after this rectifying process, you introduce W and B new parameters,
Yeah.
right?
So this
and those
W
parameters should be
original parameter.
trained, right?
Yeah, those are the already learned parameters from the model. So we're not changing the learned parameter W
Oh,
here.
I see. Oh, yeah. I thought like W and B's are like newly introduced parameters that should be tuned. Okay, makes sense. Yeah, thank you so much.
Those are the original parameters. So the only thing that we're changing here is the h of x to be the bar of hx.
Yeah, awesome. Thank you.
Yeah, thank you for that clarification question. All right, so let's move on. So far we have talked quite a bit about post hoc methods. And I think this audience question actually is a nice segue into the next part of my talk. I don't think we're able to fundamentally mitigate this issue just based on post hoc methods. And in my view, mitigating this OOD risk actually requires us to rethink how we design machine learning algorithms. So for the remainder part of the talk, I'm going to be kind of focusing more on this learning algorithm. How do we design and training this machine learning models differently? To explain what I mean, let's revisit this example. Recall that this model is trained, on this mixture of 3 classes using ERM. And so this decision boundary is, giving a perfect classification accuracy, but it can be insufficient for OOD detection purposes, right? Because the decision boundary is ill-fated. And so going beyond ERM, we need training time regularization that explicitly account for uncertainty outside the in-distribution data. And to integrate this, distribution uncertainty as a first-class construct in the learning process. And so ideally, the decision boundary should be something like the right-hand side, which is more aligned with our data density, right? Things that are more compactly surrounding the in-distribution classes. And so the question is, how do we go from the left to the right-hand side without performing density estimation P of X explicitly? Because, as I mentioned earlier, this would be quite intractable, right, for high-dimensional data. And to do so, we advocate this do objectives in learning, which is a combination of standard cross-entropy loss, which minimize the risk on the ID data. And additionally, we have this uncertainty regularization term that tries to separate ID versus OOD data, right? So this is the second term. I see another question here. This is a follow-up question to React. Maybe if you don't mind, let me come back to this question at the end of the talk, if that's okay. Cool. Awesome. So now let's zoom into this regularization term, L energy on the right-hand side, right? That's more interesting part of this equation. So now let's assume we have some auxiliary outlier data during training, which assumption that I will, again, come back to. But for now, let's say we have some auxiliary outlier training data. And so our idea here is to explicitly push the energy score to be apart between ID and OOD data. Threshold is 0. And so the effect of this, right, is to create this level set that allows us to separate the training data distribution and this outlier, the in green. And this objective has some nice mathematical interpretation too. Essentially, we're performing a level set estimation based on this measurement called energy. And if you recall how energy is defined, this is something related to this log likelihood. And the nice thing here is, we don't have to estimate P of X exactly for every single data point, right? So that's kind of a harder problem that we don't necessarily have to solve. And in contrast, all we're doing here is to optimize for this level set, which is a simpler problem to optimize for. And the result of the training is more separable distributions measured by, say, energy score on the right-hand side. And so now you can see that the FPR can be further reduced down to 1.18%, which is a drastic improvement compared to the post hoc methods. And so this is all promising, but there is a caveat to this framework. Because as I mentioned, it requires us to have some auxiliary outlier data for training, right? And so the question, which arises, where do we even collect those data from? Because in practice, collecting this large outlier training data can be arguably expensive or maybe infeasible. And moreover, this manual data collection and cleaning procedure needs to be repeated for every, ID data set if it changes. And so this solution is not very flexible. And so we asked this question, is there any way we can generate OOD data automatically for free? So that was kind of the motivating question we asked in this iClear paper. And so one of the natural idea when it comes to generation, right, data synthesis is to adopt generative adversarial networks or GAN-based generative models for image generation. But the problem there is it can be intractable to synthesize images in high-dimensional space. And so instead, our key idea here is to estimate these class conditional distribution in the feature space and sample outliers from this low likelihood region of the ID data. And this suits our purpose because we care more about regularizing models' decision boundary, but not so much, right? Not necessarily what the data points look like. And so that's kind of the key here to this method. And for example, in this case, we have the 3 clusters showing on this on the slide that corresponding to 3 different classes in the embedding space. And the dark points are the synthesized outliers, which we can use to regularize our model's loss function. And so here is the overall framework of this framework called VOS, Virtual Outlier Synthesis. And I want to mention that it's actually a general learning framework that is suitable not only for classification, but also for object detection as well. So in some sense, it's model agnostic. And taking object detection as an example, in this case, we can extract this object level feature embeddings. And then the top 2 branches are essentially performing the standard regression, right, to predict this bounding box coordinates and then this classification prediction. So that's L localization and L classification. Those are the same as how the previous laws are designed. And as this embedding gets shaped over time, we can start synthesizing outliers and then use the synthesized outliers to regularize our model's decision boundary. And so that's showing in the 3rd loss here, the L uncertainty, which is trying to separate the in-distribution objects versus the synthesized objects in the embedding space. And then during test time, we can rely on the output of this uncertainty branch to make a prediction on whether things are OOD or ID. So that's the kind of the high-level overview of how the framework works. And just to give you some concrete example here, here I'm showing you this example where the left-hand side is the vanilla faster CNN trained on Pascal VOC dataset. And I'm also listing the categories in this data set here. And without this regularization, the left hand is the vanilla faster CNN that's predicting this road sign into a train, perhaps due to spurious correlation to this color, right? And the right-hand side is when we regularize this model during training time using virtual outlier synthesis, we can successfully detect this as OOD. And here's another fun example. If you're a fan of Star Wars, this is how Lost can detect successfully the stormtrooper being OOD on the right-hand side. And our work is open sourced. Here is the GitHub link if you're interested in building further on top of this evaluation and learning framework. So I think I have about let's say 10 minutes-ish left. I also want to share kind of some thoughts on other interesting opportunities in the space. So this early work on VOS also leads to my next point, which I think there is plenty of opportunity to think about how we can evaluate OOD under more realistic data model. And so if we look back at how the field kind of started, a lot of the early evaluation is primarily focused on the Cypher benchmark, which I think it's a great start, right? That allows us to make progress over the years. But there are also limitations that we should acknowledge there, where the images are often low resolution with relatively small class space. And so this data set is not very reflective of the visual complexity that's observed in the real world. And so how do we bridge this gap? And so in the real world, images will come from, for example, much larger semantic space, also with higher resolution. And so one of the interesting question is, how can we actually perform OOD detection for this more realistic data set like ImageNet? And it turns out this problem is harder than we thought. And this is one kind of exploratory experiment that we did back then, where we showed this OOD detection performance can decrease quite rapidly as we're adding more classes to this training procedure. Right, so the x-axis would shows by subsampling different number of classes and train the model correspondingly, what's the OOD detection performance measured by AORC. And so it's kind of worsening over time. And this is because the decision boundary between our in-distribution data and OOD becomes a lot more complex, right, as our in-distribution data complexity goes up. And so one of the solutions that we put forward is to rely on this group-based OOD detection framework. I won't probably go into details here because I think the problem is actually more interesting than the solution. So if you look at this blue curve here is using our method, which kind of scales more stably as the number of classes increases, whereas the gray curves shows how the baseline approach kind of suffers as the class number increases. And so as part of the paper, we also released this data set and evaluation benchmark based on ImageNet 1K. And here's the link if you're interested in checking out and creating even better solutions. I'm sure there's a lot more creative work can be done there. And lastly, I think, as a community, we should also think about how do we better formalize this notion of distribution shift, out of distribution, and so on. And in reality, data distribution shift can happen in many subtle ways. To give you a concrete example, let's consider a training data set that contains some spurious correlation. For example, in this waterbirds data set, there are two class labels called waterbird and landbird. And they happen to be correlated with this environment E, which is the habitat that the bird lives in, right? Either being water or land, right? So waterbirds tend to be correlated with the water background and vice versa. And so if you think about this data generation process, we can formally model this data generation process by a combination of invariant feature, which depends on this class label Y, right? So this invariant feature will be related to the bird feature. And this environmental feature, which is dependent on this background E. And so that's how, you know, the input generation process can be modeled. And it has been shown that model can exploit such spurious correlation between this between the water background and the label waterbird for prediction. And so what would happen is if such spurious correlation exists and the model, relies on such spurious correlation, it would then produce a high confidence prediction for an OOD input that has a similar background, but different semantic label, right? So what I'm highlighting here is the spurious OOD, where this boat, right? The boat is the semantic label, which already changed, but the background happens to be, related to this spurious correlation. And so in this case, this OOD detector would be troubled because it's unable to differentiate this example from the training data distribution. And so this type of OOD is much harder to detect and capture compared to this conventional OOD example that are, statistically, very different from the in-distribution data, both in terms of the invariant feature and environmental feature. And so the point I want to make here is, it's very important to explicitly model, the data shift by taking into account both the invariant feature and environmental feature when it comes to detection. And just to summarize, I think I'm almost out of time, and let me recap really quick and then answer some of the questions that might be coming up. So to summarize, I started the talk by sharing with you some interesting challenges in the space of out of distribution detection, and also discuss some existing scoring functions of how we measure this notion of OOD uncertainty. And in terms of opportunity, one of the interesting question that is really worth, trying to understand further is this fundamental cause of why overconfidence issue happens with respect to OOD data. And moreover, we need to really think about tackling this problem from a learning algorithm design perspective. Essentially trying to design loss functions that allow us to learn a compact decision boundary beyond the standard ERM. And I also talk about, how we can move beyond this simplified data evaluation model to think about this evaluation task that's more realistic. For example, object level OOD detection, which is still a very challenging space. And lastly, I think as a community, we should also think about how we can better formalize and rigorously analyze this, rigorously define and analyze this notion of data distribution shift. And with that, I would like to thank you again for being here, and I'm happy to take any questions that you may have, and feel free to unmute yourself. Yep, thanks.
Any questions from the audience? You can send your question in the chat box or just ask by yourself, but I'll mute yourself.
Yeah.
Okay, I think there is a question in the chat box.
Yeah, let me maybe first answer. I think Songwoo has this follow-up question. So let me maybe read the question in the as well. What do you think of other normalization techniques that can prevent arbitrarily high activation, such as layer normalization, which enforces the latent space to be a hypersphere? That's an excellent question. So although I didn't talk about this in the presentation, but in fact we evaluated on this layer norm as well as group norm in the paper. So in short, React can be also effective when this normalization mechanism changes to be layer norm and group norm. And I highly encourage you to maybe check out the paper for details there. Yeah, thank you for that question.
Thank you. I will definitely check out.
Yeah, thank you. And you have another question I see there. Would you consider adversarial samples as OOD samples? That's another, I think, interesting conceptual question. I think I used to get that question a lot when I give the talk. The answer would be no. So if you think about this, this out of distribution detection problem is we're trying to, identify points that doesn't belong to any of this in distribution categories, right? That would look very different from in distribution classes. Whereas adversarial samples are designed in a way that's modifying on top of the distribution to, try to retain that to be similar to the in distribution, right? And so despite having that small perturbation, statistically speaking, the sample would still look, look something like the in distribution. But the goal is trying to manipulate this class prediction to be something else, right? To be erroneous. And so I would consider adversarial samples to be, still statistically, right, ID, not OOD. But both types of data, right? The commonality is that both types of, both OOD and adversarial would pose threat to the model, right? Both types of data are not good. That's something we should try to, detect and identify, which all fall under this, I think, this umbrella of trustworthy machine learning.
Great. Yeah. Thank you. Thank you so much.
Yep. Let's see. I see more questions here. So Chao Kai has this question. What's the next step when we have accurate detectors? What are the potential usage of such OOD detectors? Yeah, that's a great question. So you can think of, this OOD detector is really like a safety net, right? For a model that's, for example, already running in production. And so one of the, use case would be once the OOD is flagged, in the case of self-driving, right, then that could allow this human driver to take precaution. For example, if we go back to this example here, in this case, if we're able to put some bounding box on this helicopter, right, to be OOD, then this allows this model to flag to the user that, hey, this is something that's abnormal. And otherwise, if it passed this OOD detector to be an in distribution, then everything else works the same, right? You can still trust this class prediction. So that's one of the, the usage of OOD detector. Does that answer your question?
Yes, thank you so much.
But feel free to unmute yourself if that makes things easier. And let's move on. How does this apply to regression problem? Yeah, it's actually very interesting. Because so far, a lot of the work I would say has been primarily focused on this on classification, right? Because the notion of OOD is very well defined there. When there are categories, of this input falls outside the training categories, that's something we do not want to be predicted by the model. We haven't looked too much into regression scenario, which I think is a quite interesting problem space by itself. And I know there are quite some active work there in terms of how to kind of estimate this uncertainty, right? Uncertainty estimation for regression is also kind of a classic line of research there. And so one last question from Zhong Yi. There are some real world applications of OOD detection in real products? That's a great question. So I would say there has been a lot of interest from industry side to kind of incorporate OOD detection mechanism into production, right? I think self-driving car is one of the obvious example where this, in this high stake domains, but you can also imagine, right, in some of the low stake domains, like in, let's say in e-commerce, let's say if Amazon trains some product classifier, right, based on existing catalog of the products. But in the real world, right, there could be new products that are going to be coming up on the market. And so one of the use case of OOD detector is to be able to flag this and alert, right, of this unknown product, right? So this, maybe the business can update the catalog. So that's another kind of example. And the good news is I do think over the years there has been a lot more awareness coming from the industry side, right, to recognize, the relevance of this problem. So that's very encouraging compared to many years ago. And Francois has this question: the performance improvement when added to some existing high performance models is this a statement rather than a question?
Yeah, I think it's a statement.
I see. Got it. Thank you for that. Thank you for the compliment there. Yeah, no worries. Is there any other question? Yeah, feel free to unmute yourself.
I may have another question.
Yeah, go ahead.
So far, like most of the examples are related to computer vision and image domain data. And I wonder how you think about the opportunities of OOD detection in other data domains, such as like languages, or I don't know, but if you see any opportunities in other like data domains, or do you think it's harder to do research in that domain?
Oh, that's an excellent question. So, in fact, there has been a very active line of work on exploring out of distribution, out of domain detection for natural language processing, from, other groups as well. And recently we we're going to actually release another work, although I didn't cover it in this talk. We also kind of looked at this vision language models, right? How this two different modalities can provide complementary source of information to, help estimate this this OOD uncertainty. So I certainly think that's a very, very important, right, area of research. And so based on some of the existing exploration, we found that this observation of using, for example, right, when one question would be whether the scoring functions would translate into a different domain or modality, such as an LP. So one thing we found that if you were to use, let's say, energy score in this large language models, it's still kind of better suited than the Softmax confidence score. So the similar observation and conclusion still holds there.
Great. Thank you.
Mm-hmm. Yeah, thank you for raising that.
Yeah, I think there is another question in the chat box.
I see. Do you consider to apply your methodology for biological data sets such as DNA, RNA, protein? That's an excellent question. I don't have a direct, evidence yet, but there is one student actually who's taking my class, working on this biological data set. And we had this a chat actually just a couple of days ago. Maybe I'll have more, interesting findings to share, right, on how this OOD can play out in this structured data. That would be very interesting.
Yeah. Okay. I think there another question as well. Paper benchmark.
Someone actually
Okay.
pointed out some benchmark paper on this genomic sequence data set. Yeah, that's nice. Thank you for sharing that. Maybe you can, if you have a link, you can share with Tone down. Yeah, that's awesome.
Yeah.
Cool. Thank you for all the insightful questions.
Another question, Tom. How do you think limitation? How do you
How do you
think the
think the
limitation?
limitations of neural network models for the OOD task, do they come from both the feature representation and classifier? Yeah, so one of the major limitation, right? I think the one of the most fundamental limitation is, is what's highlighted in this slide. Is when we look at this decision boundary in terms of models prediction. Because the way that we're currently optimizing our neural networks is to focus only on the in-distribution classification, right? And so this classification boundary is actually kind of overshooting to some of the regions that are unintended. So that's what I think is the most fundamental limitation. And we really have to kind of, ideally, right? In an ideal world to design these learning algorithms to facilitate this decision boundary that's more compact. And this would give you much more conservative and accurate estimations on this OOD uncertainty. Oh yeah, thank you, Song, for sharing the links. Cool.
Okay. Yeah. Thank you, Sharon, for your great talk. Yeah.
Yeah, thank you for inviting.
Yeah, we wish when the pandemic ends, we would be grateful if you could visit us. Visit Riken IP in Nihonbashi office in Tokyo. Yeah.
Yeah, that would be really awesome. Actually, quite look forward to visiting in person
in
someday.
Japan.
Yeah, in Japan.
Okay. Yeah. Yeah, that's
really
nice.
fun.
Yeah.
Look forward to it.
Yeah, we might meet in Tokyo sometime.
Yeah, or even better, if you end up going to NERVS, at some point, we can also catch up. And thank you, Jingfeng, as well.
Okay.
Thank you for a great talk.
Yeah.
Thank you.
See you. Bye.
Bye, everyone.